Doing well.
Good. I got thinking, last week at the end of class, I asked how I'm doing, and you guys keep giving me thumbs up. And that's kind of not the answer I want. I'm really asking, what could I do better? Okay? And in particular, one thing that happens in this class is because we have such a wide diversity of students, sometimes I'm talking about things that are boring one student and another student's lost. And so in particular, I'd like you to pay attention to that, of where you might have felt bored or you might have felt lost. And because I'd like to get feedback on that. I want to figure out how to do that better. So as classes go on, and I'll continue to ask at the end of class, but that's one thing in particular I would like feedback on. I believe I'm a pretty good teacher, so I don't need all the thumbs up right at the end of class. Okay, I live fine without those. Okay, but what I'm really looking for is how to do a better job on certain parts. Okay, so wanted to mention that. So we're going to talk about an energy thing. So it's kind of, so who takes care of the National Weather Service? It's under a bigger organization.
NOAA.
What?
Is it NOAA?
NOAA, National Oceanic and Atmospheric Administration. Okay? And they also worry about this other thing we're going to talk about. It's this other kind of weather. So this is kind of a test of how much you've been reading the news. The sun's been in the news this week. Does anybody know why?
I haven't seen it in the news. Which is this in the news?
The sun.
The sun?
The big bright thing in the sky.
Right.
It's been really in the news this week.
Are there some solar flares going on? Or?
You're guessing, yeah, but that's okay. No, guessing is okay. And it is. We've had solar flares this week. Okay, there was one on Tuesday and another one on Wednesday. And this is all just going to tie back into the electric power grid here in a few minutes. Okay. So one occurred on Tuesday and one occurred on Wednesday. And what happens with solar flares is they can detect them. They watch sunspots, so they come out of sunspots. They can detect when they happen by seeing them visually. So light, which takes like 8 minutes to get here. Hi, are you Naomi?
Naomi.
Yes, come in, come in. I'm Conwell. Naomi's joining us. In fact, we'll let her do a little introduction. She's kind of coming from a special place here. Okay. Would you like to introduce yourself a little bit?
I'm Naomi Lubeck. I'm a fellow at the Center for Environmental Journalism. It's called the Scripps Fellowships. And I'm looking at a renewable energy topic for a book that I want to write. I usually live in Stockholm, Sweden, but I'm from California, so.
Okay. So last year when I taught this class, we also had a fellow from with the same program. He was writing a book. He was a Japanese journalist that was here. He was writing a book on Fukushima, the nuclear reactor disaster. Okay, and he offered all sorts of insights from a different view. Being an author and a journalist and those sorts of things. That's different than engineers. Okay, so, and feel free to ask questions too.
Thank you.
We were just talking about what's been in the news this week about the sun. The big sun up in the sky, okay? Rocky took a guess and was right. Solar flares, we've had solar flares this week. And turns out there was one Tuesday and a bigger one on Wednesday. And they can tell when they happen by the visible light, okay? But it's this big mass ejection of particles that take 2, 3, 4 days to get here, okay? And today is Friday, yesterday was Thursday. The particles from Tuesday's storm got here yesterday, okay? One thing it does is gives you a really nice aurora borealis, okay, the northern lights. And in fact, there's reports that they saw the northern lights as far south as Arizona. There are pictures of them last night, okay? The particles from the second larger solar flare are supposed to get here today and tonight. Okay, that's going to be even bigger. So Rocky and I were talking about, he says he's going to stay up late tonight. You want to step outside, and it looks like it's going to be clear. You want to step outside and look at the aurora borealis. Okay, because it should be spectacular. It really should.
Yeah, what time it should be?
I think it's pretty much going to be continuous all night. But, you know, an after dark sort of thing. There are some different colors. I'm going to go to some websites here that will tell you more about it, too. You know, I lived up in Montana when I grew up and would see the northern lights then, but I didn't pay a lot of attention to them. So I'm going to be looking tonight. But what's happening, the physical mechanism of what's happening, what causes the northern lights to be so bright? You got all these charged particles that were emitted from the sun 3 or 4 days ago, and are finally getting here to Earth. Turns out if you go and search for space weather, that's what this is called, space weather. Okay, here's NOAA, today's space weather. NOAA is, they take care of the weather on Earth, but they also take care of space weather. And space weather, let's see here. I think this is the one I want. Okay, the second of the expected, let me see if I can enlarge this first. There we go. Second of the expected coronal mass ejections has arrived. Good prediction with the expected time. Second one's stronger than the first. Okay. You're going to see it on the 13th. Through the 13th, that's tomorrow. Okay. So this gives you all sorts of information about it. And in fact, where did I see? I don't find it now. There's some maps that plot where the northern lights and the southern lights are going to be. But why does this, what does this have to do with the power grid? So why, let's go back to another question. Why are these lights, so we got all these charged particles, massive amounts of charged particles, and their Earth is going, they're coming right at the Earth and we end up colliding, okay? Why do we get northern lights and southern lights?
It's intercepted by the magnetic field of the Earth.
Magnetic field of the Earth, okay. So you get these charged particles, and it starts moving charged particles, and a moving Earth, and a magnetic field. And we're going to talk a little later here about Faraday's law, about currents being induced. Okay? It turns out if you have moving charges through magnetic fields, you can get currents induced. And in fact, if you have a conductor moving through a magnetic field, you can get current induced. There's a whole bunch of variations. We'll talk about them. But what happens is, as you have this huge amount of charged particles, as the Earth moves through it, you get currents induced in all sorts of things, and mostly in conductors. And where do conductors come into the power grid?
Transmission wires.
Transmission lines, big, long, nice lines. Transformers, these big windings. Okay, and so these things can be strong enough that they can induce significant currents in the transmission lines and even in the transformers to melt them and destroy them. Okay? One of the reasons that NOAA works so hard at this is because, and they now have a prediction where they can predict plus or minus 6 hours when it's going to hit. But if you take transformers and transmission lines offline and ground them, okay, you can reduce the effects of the currents. If you don't, you could have your transformers start melting, and we don't keep spares around. Okay? And it's the sort of thing where the storms could actually destroy our power grid, and it would take us months to get it back online. Now the sun goes through this, I think it's an 11-year cycle of sunspots. Okay, and we're pretty much at the peak sunspot activity right now. Okay, and so they expect more solar flares. The other thing that comes into play here, if the solar flare is on the other side of the sun from us, it's going to go away from us. Okay? If it's on the edge, it's going to be at 90 degrees from us. Okay? This one, well, in fact, these two came from the same sunspot. And the sunspot is pretty much, as we look at the sunspot's right in the middle of the sun. So if it comes out radially from that, we're right there on that extended radius. So all this is coming at us. And they expect it to hit more of the northern part of the Earth than all of us. Back in 1989, there was a big solar flare. Ended up hitting Quebec, up in Canada. They, in fact, took a lot of the power system down. It induced severe currents and things. It was especially bad because that part of Canada has this, and there's a name for it, but it's this bedrock, a solid base of rock that goes for hundreds of miles in every direction. And it served to make a really good ground plane, which caused the currents to be induced even more. The other thing that's going to happen is pilots are being told, and airlines are rerouting their aircraft around away from the North and South Pole, because that's sometimes the shortest route, is to go over the North Pole. But radio communications can be affected. But go outside tonight, look at the aurora borealis. If the lights start blinking, we'll see what happens. Anyway, questions on that? Yes?
How big does a solar flare have to be to really impact the Earth? I mean, is there a magnitude, and are they usually that big?
They have magnitudes. In fact, they have a whole scale of them that is on this. I searched for space weather, a National Weather Service. There's, let me see if I can go find, there's several of them here. There's also a spaceweather.com. but there's a whole category of strengths, just like there are for earthquakes. Okay.
Where would you go find how often these things had impacted the electric grid? Who would track that?
NOAA.
No.
NOAA, yes. Very much. If you go to Wikipedia, did I get that when I searched here? Live. Some in-depth articles here at the end of the Google page too. National Geographic, that article was really pretty good. There'll be information on Wikipedia of what happened in Quebec in 1989. Turns out the strongest recorded solar flare happened back in 1860s or 70s. A couple amateur astronomers saw it, but I was just reading about it. In fact, I think it was in the National Geographic article that it affected the telegraph system. Something terrible. So telegraph system basically is, you got these long wires and you got a battery at this end, okay, and current flows, and your key, you send current pulses or you don't send them as you do the key. Well, the space weather, the solar flare was affecting the telegraph wires so much that they could disconnect the battery and still send messages, okay, because there were all these induced currents in the wires. But this we talk about terrorists doing things to the electric power grid, and they could, but there's other natural causes too that could be just as severe. Any more questions, comments?
So for prevention, they would literally just shut down the entire power grid if they thought it was going to be serious?
Yes, that's what they would do. Shut the power grid down, ground the ends of the transmission lines, ground the transformers, so that any induced currents were not propagated through the system. So yeah.
How much does a transformer cost?
A few $1 million.
That's why we don't keep extras.
No, that's why we don't keep extras. Transformers and substations, we're going to talk more about substations to look at some of the size of them. If I took a transformer from and we're talking, so there's transmission substations and distribution substations. Transmission substations are often more about connecting various transmission lines and rerouting the power through the lines. Distribution substations are going to be stepping the power down to a lower voltage, but they have good-sized transformers. I taught a class this summer and took the students on a tour of a substation in Fort Collins, and the substations they were pretty tall, but if you laid one down, it would about fill up half this room, just about that size, okay? And they're very expensive, and they also tend to be custom made. I've mentioned that the United States government is developing a one-size-fits-all transformer that they can use for replacement, and they've even done some experiments to see how fast they can swap those out. Okay? Any more questions on that? Comments? Yeah.
How long would if they did have to shut down the power grid, how long would it have to be for?
Probably just a few hours. Yeah. I was reading about their prediction system, and they say that they can predict now, NOAA can, plus or minus 6 hours. Last time they predicted one, they were within 45 minutes. Okay. And it's going to depend a lot on how long the flare was, long in time, because how far it stretched out in space. It also depends very much on the flare versus where the Earth is. And it also depends on which side of Earth is facing the flare when it actually hits. Okay. They do a lot with that, though. Okay? What did we talk about last week?
Power factor.
Power factor. Okay? Somebody want to give me a summary of what power factor is?
Kind of the proportion of power that's real versus imaginary. Well, it's not perfectly proportional, but it's got the Pythagorean theorem going on.
Okay, that's a good start. It's often called real versus reactive, but mathematically we treat it as a real part and an imaginary part too. Okay, so the real power, that which is doing useful work, is here. The reactive power, which is not doing useful work, it's being stored in magnetic fields and electric fields. It's causing real currents to flow that generate losses, but it's not doing useful work. Okay? And the total apparent power, square root of some of the squares of those, and this is what you need to size the equipment for. Because you have currents that size, even though you're only doing useful work with the real power. So when I say useful work, we've talked about resistors. And resistors, they turn electricity into heat. Now, is that useful work? Monica's saying no. I heard a...
Trying to heat a room.
Trying to heat your house, yeah. Okay. If you're trying to cook your dinner, okay. We tend to think of heat as, heat is the least useful form of energy. And electricity is quite high. But if we take and run a motor, there's going to be some reactive power there as the magnetic field grows, expands, and contracts. Okay, but there's going to be real power too. Part of the real power is because of heat losses in the windings. Where does the majority of the real power go, though?
Whatever the motor's doing.
Whatever the motor's doing. If it's pumping water, if it's lifting a weight, the motor is basically a mechanism for converting this electrical energy into rotational energy. Okay, and that's useful work. And so that is part of the real power when you do the calculations. Okay? Questions? We went through this. I'm just doing a quick review here because we're going to come back to power factor again and again and again. There's the power industry view that, yeah.
Well, it makes more sense after you've had a few more beers.
If you've had a few more beers, yes. If you like, and I'm mentioning this for you, Naomi, that if you talk to power industry, people in the power industry, they'll describe VARs and watts and stuff with the barrel analogy, and it stinks. It's a terrible analogy. But if you go into Google Images and search for power factor, you will get millions of pictures of beer. Okay. So the one thing we didn't talk about on this slide set, this is the last slide, was Synchro Phasers. Okay. We talked about phasers. What do phasers do? They're kind of like vectors, but in electricity, they've got some other properties. So what's a summary of a phasor?
Shows the phase offset of voltage and current.
It can show the relationship, the phase relationship between voltage and current, or different voltages even. Okay. The phasors have a magnitude, and they have an angle. Okay. Now, if we take, that's the second part of the word. What's the first part of the word? Synchro. What do you think of, or what might you think of when you talk about synchro? Synchronization. Synchronization in what aspect? Yeah.
Because that's what I thought of when I heard synchro. I don't know the context to apply it to.
No, you're right on with where you're going.
So I guess applied to this, it would be, I imagine the synchro phaser would be in some ways a combination of different phasers to see what it's almost like vector dot product, where you're finding out for the phasers what components are in the same direction or synchronized.
Okay. That's a possibility. That's not really what happens here. Synchro phasers is about being synchronized, but it's about taking phasor measurements at the same time, synchronizing your measurements. Right now, with the electric power grid, if I wanted to make a change to the power grid, I'm an operator, and I'm gonna, drop this transmission line, or even do some more minor thing. I would really like to be able to predict what it's going to cause. Yeah? We can't. We cannot calculate its behavior in real time. And in fact, even in given a lot of computational power, we cannot reproduce what its behavior was given at a certain state. Okay? And as the power grid, as we start doing more renewables that add variance to the power grid, the clouds come behind the clouds block the sun from the solar panels, and the production goes down, you're going to get more variation. And you want to be able to adjust for that. So what synchro phases are, and they're spread, and they're also known as PMUs, phasor measurement units. They measure voltage, current, and frequency, and they're basically a piece of equipment. And you put one here, and you put another one over there 100 miles, and another one over here. Often put them in substations, but they give you those measurements at a certain location, and so you spread these measurement units throughout the power grid, and time. So they will give you a measurement and a very exact time of when those measurements were valid. And the time tends to need to be within about a microsecond. So all these units out here are measuring voltage, current, and frequency, and they're not doing it at exactly the same time, but they are doing it synchronized to a master clock, and there is less than a microsecond of error in when they when they make the measurement. So they timestamp it with this 1 microsecond. Now you get a whole bunch of measurements over the power grid that you know exactly when they occurred. And now you can start predicting what's going to happen or what did happen. If you go look at the blackout, I think it was in New York before most of your time. Okay.
I think I was there.
Yeah, that's why I said most.
That was in the airport in New York. The one in like 2000.
No, this is back in the 70s, I think. Okay.
77.
There were a couple.
Yeah.
There have been a couple.
Well, yeah, there have been. And these are, if you go to Wikipedia, you can find links to really good discussions of these blackouts. But that blackout happened, and it started way over in Illinois because some branch fell against a tree, or a line. Some branch fell against a tree. Some branch fell against a power line and caused a short. And this caused this to happen. And we're talking over periods of 5 minutes, 10 minutes. Things start to get worse. And if you go look at the reports from these things, invariably the reports say better operator training, okay, and keep the branches cut back from the power lines. Okay, they say that a lot. And if you read close, what they're really saying, is they don't know exactly what happened. Okay? But it was probably related to this. But if we now have these synchro phasers and these measurements, and we get a disturbance over there on the power grid with our synchro phasers, we can say at this time we started to see a drop in the voltage level or a change in the frequency level there, and that happened before the one over here happened. So it was closer to that. We can't say that now. Okay? So synchro phasers are starting to be rolled out. The Western electric grid, and we'll talk about the different parts of the grid here in a minute, but the Western, this is basically west of the Mississippi, is doing a rollout. I think they've got 100 to 200 of these synchro phasers, but then they generate a lot of data. So there's a lot to do. But these are very important. The other interesting thing about this 1 microsecond is because of it, there's whole new standards or whole new protocols for measuring time. And it's synchronized to GPS satellites. Okay? But in order to get that 1 microsecond, because if you don't get that 1 microsecond, the error in your voltage and current frequency readings is too big, and you can't tell what's going on. Yeah, Cam?
It's very useful to determine what happened on the grid. If you're doing measurements on the order of a microsecond, are you doing measurements? I guess you can't be doing it every microsecond.
No, you're not doing it every microsecond. You're probably doing it every, at most every few seconds. Okay? But you're making these measurements and you're recording them. They're all being sent to a central place and being recorded. And one of the issues is how often do you make the measurements, because you're saving this data. And the more data and more data and more data, and this gets back to the big data situation again. Okay, so you're making measurements that are accurate within 1 microsecond of your time base. And everybody's sharing the same time base. Okay, but you're not making them every 1 microsecond. You're making them less frequently than that. Okay, and disturbances in the power. One sec. Disturbances in the power grid don't happen. They don't propagate super fast. If you look at propagation, it has to do with some constants, permeability and permeativity of materials and of free space and stuff. Okay.
I just wanted to clarify, it sounds like there aren't that many right now? Is that
There aren't that many right now. They're rolling them out now. It's new technology. It's probably been in the last 5-7 years that they've started to do pilot projects.
And these are, you have to forgive me, I have a very poor understanding of
No,
your-
that's no.
I mean, does this mean that there's one central place that this is all being modeled, or somebody who's handling this data and storing it, and then making heads or tails of it?
So basically, let's see here if I'll get to a map, but basically they're spread out. Figure 150 of them spread out in the western United States. So they're pretty far apart. And they send their data to, I can't necessarily say a central place, because the western United States is broken up into a bunch of utilities. Okay? And one of the big challenges was getting them to agree to share their data. Because in sharing their data, other utilities can find out what their power flows were, and you get into marketing. Marketing electricity, which is something we'll talk about in much more detail. Anybody remember Enron? Did anybody besides me own Enron stock when it collapsed?
That was the smoke and mirrors thing, right?
But it went down and I got out barely before it got to the bottom. I only had $2,500 in there, but I think my $2,500 turned into $700. Energy markets, they manipulated the markets, and we'll talk more about that. If you go into a major utility or a transmission authority that controls transmission, they make you sign something that says you're not involved with the marketing of energy. Because if you go in and see their map, and they have these huge video displays, huge, like the length of this wall and 3 times as high. And these people can go in and look at that and see what power flows are happening and make money off it. Okay? So, you know, what happened or what's happening. Did I answer your question? I don't know.
Sort of. I mean, it sounds
Ask
like
it
it's sort of
again.
a mess.
What?
Nobody really has a view of the whole grid, is what you
Nobody really has a view of the whole grid.
So how come somebody told me today about the San Jose transmission that somebody sabotaged? Do you remember this story last year? Somebody just hit a power station to take it out to see what would happen.
Was this the one in California?
Yeah.
In February? Yeah. Was somebody shooting at the transformers? That one, yeah.
And the way that they were telling me about this is a warning signal to all the people that are running the grid that this is a problem and that there are 7 nodes in the U.S. that could take down the whole grid. But it doesn't sound like the grid is that interconnected to make sure that you could.
It is that interconnected.
But it's not that intermanagement connected.
Management-wise, the management is split up. But even if it were managed under one authority, and there are authorities, there's FERC, the Federal Electric Regulatory Corporation, or maybe that's energy, and there's NERC, that are 2. And so they have oversight, and in fact, NERC used to be National Electric Reliability Corporation, and now it's the North American Electric Reliability Corporation because it includes Canada and Mexico. And it used to just have authority to make suggestions. A few years ago, after some big blackout, it was given authority to say what you're going to do and fine you if you didn't do it. Okay, so there are some larger authorities like that, but our ability to know what's happening first, so if something's going on, say somebody's starting to take out a transformer or a substation, or there's just a big storm coming through, our ability to know what's happening is not where it needs to be, and our ability to predict what's going to happen, should we make a change or not make a change, we don't have that ability in real time at all. Okay. The grid tends to, there's this thing called N-1 contingency. A very important thing. The grid at all times is supposed to operate at N-1 contingency, meaning that any one resource in the grid fails, a power line drops, a generator goes down, okay, it will still remain running. Okay, if you lose 2 things, you're hosed. And so the operators tend to watch it and say, they have to operate within these limits that say, for instance, I've got all these transmission lines, this one's carrying 50 megawatts. If it suddenly went down and I had to move that 50 megawatts to other lines, do I have enough capacity on all the other lines to absorb it without getting a cascading failure? Cascading failures are what start to bring it down. Something happens here, then this power line starts to get more power, and that doesn't affect it right away, but as power lines start to carry more than they're rated for, the power lines after, and there's in fact this 5-minute limit where you can exceed the normal rating of a transmission line for 5 minutes. But after 5 minutes, it's getting so hot, and it's sagging and sagging because it's getting longer and longer, okay, that it's potentially will touch something, or it will permanently damage the transmission line. And so all these things need to be managed. It's an interesting problem. I'll go off a little bit on one of my soapboxes. Okay, global warming. Okay? How many of you here believe that humans are causing global warming? Okay? Okay. I tend to be agnostic on the subject. And it's, you know, and I love talking about it, so if you want to talk about it, I'd love to talk about it. Okay? But one of the reasons I'm agnostic is here we have the electric power grid, which is something that we as humans created. It's a human construct. It abides by a whole bunch of physical laws that we understand pretty well. And yet we cannot successfully model the behavior of the electric power grid. And I've done a lot of computer modeling in my life. And so I struggle very much with believing that we can successfully model the effect of what the temperature is going to do based on things changing on the Earth. Okay?
Are we allowed to argue with you now?
You're always allowed to argue with me.
So what about the idea that you can figure out these equations that tell you how things will behave to a certain parameter? I mean, the electric grid is also governed by physical rules, right? So
Okay.
the idea that greenhouse gases also obey physical rules and that you can make general large-scale models. The models are never right, but they are useful, right?
And see, and that's where I question it.
Why?
To me, a model, when you do a model of the power grid, okay, you're actually saying, we understand these relationships between voltage and current and capacitance and inductance, okay? And understanding those relationships, we're going to put them in a model. Okay, and the model is only as good as our understanding of the relationships. Okay. Now, electrically, we tend to understand electrical relationships pretty good, wouldn't you say? Monica's one of our double E's here. Okay.
That's Rocky.
That's me.
You're yeah. You're an ME.
Okay.
Okay. So, I'm sorry. I keep doing that with you. I don't know why it is, Monica. Don't you think we have a pretty good feel for the relationship between different electrical parameters? And
It seems like we know a lot of it pretty well.
yeah, but yet even knowing those relationships, we cannot model it. Okay.
Not even to a certain extent that will give you a rough idea of what's going to happen. A rough idea. That's all I'm asking.
If there's a disturbance, okay, so there's also two things. There's two kinds of models. There's a steady state model that when it operates and everything's stable, easier to model. When you start doing transient analysis, okay, when it's changing, things get a lot trickier. Okay, and I don't want to get in a big argument. Like I said, I'm agnostic. I don't know. I really don't know. I don't trust the models very well because of my experience with modeling. Okay, and my experience with how a little change in a model can have a big difference. And so that's one of the things I have. Okay, and as I work with the power grid, the fact that we can't predict what's going to happen on the power grid makes me wonder how we can predict what's going to happen on Earth's climate. And I'd be glad to talk with more of you this online, offline.
I want to ask you just one more thing about that.
Yeah.
So how much data do you think that you'll need in order to get a good model? After they put up these Synchro Phasers and things like this, how much would you need in order to figure out what the grid is actually doing?
Well, so there's data. You need data. You need to have a good understanding of the relationships. Okay, and often Newton's laws were pretty good. F equals ma, right? And then Einstein came along and we found out that Newton's laws were just an approximation, right? Okay, that if we start to look outside this narrow set of conditions that Newton was, then those relationships don't apply anymore. And so I tend to struggle to believe that we really understand the relationships as well as we need to. And the other problem that comes up with a power grid is it's nonlinear. And solving nonlinear, finding solutions to sets of nonlinear equations is hard, isn't it? No?
I took a class called Inverse Methods, and you can kind of linearize pretty much any nonlinear system you want.
So, are you talking about operating it in a linear region?
I suppose not, but just if you have like a nonlinear equation, you can find ways to linearize it, or at least approximate it pretty well.
So that's the magic word there, approximated. Yeah. So there's all these questions, and like I said, I don't want to get into this and have a big discussion on climate change.
I don't want to talk about climate change. I wanted to know what you think we need for a grid in order to understand what's happening. I mean,
we need.
What is the ideal?
We need a lot more data points than we have. We need to understand the relationships between variables a lot better than we do.
Like the network layout?
When I say relationships, often we represent relationships as equations. That this, I can write an equation of the voltage is related to the current this way. Okay? And we need a lot more computing power. Okay? And especially to do it real time. Yeah, Kim?
And just kind of talking on that point for climate models to predict weather phenomena a week out, we haven't gotten to computing power. It's projected to happen within the next 5 years or so, where we can predict weather for a week locally. But the problem you run into with large systems like this is even if you have all the information you need, like all the data points you need, because they're transient systems and you're relying on these things changing over time based on the conditions that you're measuring at these data points, they're all going to be somewhat chaotic. So any uncertainty you have in that initial data is going to lead you to a conclusion or lead you to a prediction that's flawed because you can't ever be certain that even the data you collect is accurate. So there's not the more reasonable thought process is that you'll never be able to accurately predict the way such a large, complex, non-linear, and transient system is going to behave. You can get better and better predictions, but it's just not possible.
Yeah. And your mention of chaos or complex systems, a tiny little change can cause a tiny little change in the input can cause a huge change on the output. Okay. So one more here. How many of you heard of Karl Popper? Heard of Karl? Okay. Karl Popper was a science philosopher, and he said, "How can we really tell if what we're talking about if we make a prediction?" Okay, if we have a theory, okay, what are the characteristics of a true scientific theory or a true scientific prediction? Okay, and he came along and said, it has to be falsifiable. There needs to be tests that you can do that could prove it wrong. Okay, and if there's no test you can do to prove it wrong, then it's not a scientific theory. The example I like to give is Einstein's theories of relativity. One of the things he predicted, so he made predictions, and now you go try to test these predictions. Okay? He made the prediction that if a star was moving behind the sun, that the gravitational field of the sun would bend the light coming from that star. And 20 years ago or so, they were able to test that because we had a full solar eclipse. So boom, the moon's blocking out the sun, and here's this star that's moving right behind the sun. And lo and behold, it moved, and it should have been behind the sun. You could still see it for a while because the light was being bent around. So he made a prediction that could have turned out false and would have negated the theory. The reason I bring this up, this can apply to a lot of things, and I often think about it, is sometimes come up with climate change. We're making predictions. We can't really test them now to see if they're true or not, or false or not. But anyway, enough of this. I'd be glad to talk to you more offline. Yeah. Oh, yeah. And I'm agnostic. It means I don't know. Okay. I'm not a denier, as the extremes call it, or an alarmist, as the other extremes call it. Okay. But I find the topic fascinating. Okay. And a lot of it is because of my modeling experience and having to do with the models. So, any other comments on that before I move on? Any comments in general about my stand, or did I wander too far off? Go ahead, Monica.
I was just wondering, because you see global warming from like a modeling standpoint, but then there's data showing that the Earth is actually warming up, and I was just wondering what you make of that. Anyways, just maybe it's unrelated to humans, is what you're saying?
Well, and so one of the big questions in global warming, how much of it is natural variance, and how much of it is human caused?
There is natural variance.
There is natural variance.
I think that in the Ice Age kind of part of that is just
Yeah.
at times the Earth was much colder.
Yeah, and so there's cycles. Some long-term cycles, there's small-term cycles, okay. But one of the struggles with global warming is separating the natural variance from the human-caused variance. And it's a struggle. Everybody struggles with it. And there's both. It's just which is dominant. Yeah, Kim.
One clarification. You say that you're agnostic insofar as you believe that you can't know, or would you say that you're a skeptic insofar as you're doubtful that we do know? To me, agnosticism is still somewhat of a belief. You would just believe that it's unknowable, whereas the skeptic would be someone who just doubts the veracity of claims being made.
Okay, good philosophical discussion here. There are math, that's been demonstrated, there are math problems that cannot be solved, that we cannot know the answer for. For me, I don't think that we know now. I'm not going to say we can't know in the future, okay? But for me, right now, I consider myself an agnostic in the moment who, and I've been other places, and I pride myself on my willingness to change my mind when other data comes up. So I'm an agnostic for the moment.
Can I ask you guys what you think? Is that allowed, or should we do that later over beer? We're going to talk about the variance and that's all. Beer. Never mind.
I would say that what we've seen in the past since industrialization is the rate of change of temperature that we've seen is beyond the scale and can statistically be shown to not be naturally varied.
You're saying it's dominated by human influences.
That's what I do.
Okay.
I think that as well.
I kind of feel like there are ways to test things right now. You can look at volcanic emissions and other things. I think that the next time we have this discussion, you should bring in Jim White from the InStar over here on campus.
Okay.
That would be really fun.
And this is not a global warming class.
Yeah.
Okay. It's, I read a lot on it. It's the politics going on with it are fascinating too. Okay. But
Well, can I interrupt? Because the policies that will directly affect the electric grid are going to be made according to what people think about climate change and whether it has to be addressed, right?
and in fact, we're going to talk about those sorts of things. We're going to look at a case study here in 3 or 4 weeks about Germany and the policies that Germany has. Okay, and their move to renewables, and their move away from nuclear. Okay. Did you know, by the way, that in Germany, and I think all of Europe, burning wood is considered renewable?
Huh, it grows back.
Yes, exactly.
You can grow more.
Yeah, you can grow more.
Actually, I had a project to do something with the beetle kill trees in Colorado.
Okay.
Create a different source of energy from it. So I guess it's
Yeah.
renewable.
Say it again. Your project?
Project to convert the heat or whatever from the beetle kill trees.
Yeah. So like there's a plant that takes all those trees and burns them to make them into heat for the electric grid. I mean, it's transformed into.
Yeah.
That's near here, right? I mean, this is near
So they've
Fort
already been
Collins.
killed by the beetles. And
Yeah, they just take the wood and
then
then
they
burn
might as
it.
well.
I was wondering if there was any clause in this European statement that burning trees is renewable and that you have to plant a tree as well for carbon sequestration.
I don't know.
Yeah, I was thinking that too.
Yeah, I don't know.
It's not renewable if you actually do plant those trees. It's like, well, you could, but are you?
I know one reason it's there because there are financial incentives to go to renewable. Okay? And so if burning biomass is what we're really talking about here, I say trees, but burning biomass is considered renewable, then you get this additional financial incentive. Okay, and so the politics is interesting. Okay, and we'll find the same thing in the electric power grid when we start talking about we've got several different kinds of power plants that all produce power, and they all have different costs, and we may even get to the costs today. If not, we're going to look at the cost comparison between different kind of plants. And which one do we turn on first when we need power?
Right.
Cool.
Whoever's cheapest.
Whatever's cheapest.
Natural gas here.
And we'll look at the numbers and we'll talk about it. And that's been the policy for a long time, whatever's cheapest. But suddenly, it's getting more complicated, and we'll talk about that, but not right now. Okay. But I'd love to talk with you, any of you more offline about this. It's a fascinating topic that we've all got more to learn about, I believe. We really do. Okay, we're going to talk a little bit about magnetic circuits. Just briefly on those. They probably won't come up. We're going to talk more about transformers and the role they have, and then we're going to talk about three-phase. Who invented three-phase power?
Tesla.
What?
Tesla?
Tesla. Nikolai Tesla. Okay. I was just reading a biography about Tesla. It turns out he was OCD and liked to do things in threes. Okay.
Is that like three-phase?
I suspect there's some relationship. His patents and his development was really polyphase, multiphase. But three-phase is, in his mind, the best implementation of it. And, but I just found it interesting.
Like, say, 2 or 4
What was that?
5?
Yeah, you can do more phases than three-phase. And he developed all the theory behind all that. Very much a theorist as well as a practical person. But Nikolai Tesla. So we're going to talk about three-phase too. The magnetic circuits are covered in section 2.4 of the textbook. Okay. Magnetic equations. We don't have any physicists in here, do we? Anybody study electromagnetics from the physics department rather than the electrical engineering department.
We all have to take
That's
this
done
too.
from each.
But,
Too, but that was circuits.
It ended up making more sense for me in the electrical engineering department, but
yeah, it turns out the physicists and the electrical engineers use different notation. Okay, the electrical engineers use B, magnetic flux, flux density, and H, magnetic field intensity, while the physicists don't use B. Okay,
what do physicists use?
they're related by this constant, mu, the permeability of free space. Okay, but engineers write the equations so they have both terms. Okay, I once got a shirt. Okay, I did my work in electromagnetics. I got a T-shirt that said, "And God said," and then it showed Maxwell's equations, the defining equation for electromagnetism, and then it says at the bottom, "And there was light." Okay. Problem is, there's two variations of T-shirts, one for physicists and one for electrical engineers. Okay, but magnetic equations. So we're going to really do here a pretty quick look at how magnetic equations are very similar to electric equations. And I'm bringing this up because when you start doing things like transformer design, motor design, they all become magnetic circuits where you have magnetic flux flowing. Okay? And we're going to do this, and this is not something you're going to be tested on. But it's something that I wanted you to understand. At least there's this whole other field. There's this thing called reluctance, R. It's analogous to the resistance. The reluctance of a, if you consider the magnetic flux as if, in fact, I think the next, I'll do her. Flux is analogous to current. Magnetomotive force is analogous to voltage. And it's in fact equal to the number of turns times I. So we get a very, just like I've talked about hydraulics, we've got the flow of something, we've got the pressure pushing it, we've got a similar thing on magnetic circuits. Right-hand rule. Still remember taking my electromagnetic class, and there was a guy, Tony, who was always struggling with it, and he's over there holding his pencil in his right hand, working on the test, and he's doing things with his left hand. I'm just, right-hand rule. If current is flowing in a wire, here, and I point my thumb in the direction of the current, my fingers show the direction of the magnetic field. Or if I know the magnetic field's in a certain direction, I can use my fingers and my thumb points and things. Okay, this one's easier. It's interesting, I've mentioned technicians, current goes the other direction. Have I mentioned that in here? Did they assume the current flows out on the negative side of the battery? If you go look at technician electrical books, they do not have the right-hand rule. They have the left-hand rule. They really do. Okay, so be aware of that when you're working with technicians, because they assumed the
Why?
Because it's electrons that flow in that direction. But electrons are negative.
yeah.
So the positive current flows against the actual flow of electrons.
So Ben Franklin
I've confused Everett ever since.
knew that one kind of particle were flowing for the current. He didn't know if it was a plus or a minus, so he picked one, and he was wrong. Okay, but that established the whole basis for electrical engineering, and it's been the convention ever since, because it doesn't matter in the math. But now that we know the technicians,
Part of the math to concepts for some people.
yeah, and so engineers, the fact that we're doing with math and it's the signs all work out and everything. Technicians, they're more want to know physically what's going on, so they worry about the real flow of particles. So if we had an electromagnet here, I used to play with these things when I was a kid because we didn't have computers. I truly did. This flux, these magnetic field lines, are like the current. The magnetomotive force, that pressure that's pushing that flux, is the current times the number of windings. So I can build a magnetic circuit and write equations that are pretty much identical to Ohm's law and all that stuff, and I can solve it. And when you're doing transformer design and stuff, you got to do this. It comes up a lot. So the equivalent of Ohm's law is the magnetomotive force is equal to the flux times the reluctance. Now, the other right-hand rule, okay? Cross product? Yeah, it's cross product. B cross B, okay? You talk about cross products and dot products a lot.
Yeah.
Do you use them a lot?
Graduate ME math courses and a lot of fluids. So, yeah.
Fluids, okay, comes up on fluids?
Oh, I've always just done it as this, and rather than point the middle finger down, it's just coming out of your palm.
So we'll get it here. We'll use the room here as an orientation to get this all. Basically, if I've got a magnetic field coming out of this wall and going out that wall, okay, my index finger here points the direction of the magnetic field. Okay? Now, the thumb points, now, so if I have a wire, I've got a wire running this direction, from that wall to that wall. The magnetic field is going that direction. Everything's going to be at right angles here. We got this wire. Now we take this wire and we start moving it. We can either move it up or down. Okay? And if we do it, we're going to get a current induced in that wire. Okay? And the right-hand rule says if the magnetic field's that way and the movement is that way, the current's going to be that way. Okay? This comes up in motor design a lot, and in fact the other part of it is if I have a magnetic field going that way and I have the same wire going across, and I put a current through the wire, I can cause a force on the wire and cause it to move. And if we look at motors, that's exactly what happens. We have a magnetic field, we put a current through a wire, the wire is basically perpendicular to the magnetic field, and we get a force, and it rotates. Okay? Faraday's law. So we've got magnetic field flowing between north and south, and I can never remember which one it flows to. Okay? But we've got a magnetic field going this way. Okay? We've got rotation here. So these wires here are moving through the magnetic field, and it induces a current. And it turns out, in this case, it's sinusoidal. So this is an AC generator. Faraday cage. When did we hear about Faraday cages? We talked about them first day class.
Yeah, we did.
Yeah, we did. The helicopter. There's a video we watched on the first day of class of how they service high voltage transmission lines while they're still active. It's linked on the D2L stuff. But Faraday cages. You can Google, you can search images. And in fact, Faraday cages, Tesla did a lot with Faraday cages. I'm not going to Google them for you. Okay, I'm running behind. Imagine that. Here's a little more magnetic digression. Magnets, they're dipoles. They always have a north pole and a south pole. There's been speculation that we could have monopoles. where there's only a single pole, single north or a single south pole. And in fact, they've come up with some materials recently that internally can have monopoles. Anybody read science fiction? Larry Niven? Larry Niven?
Long time.
Oh, it's been a long time with Larry Niven. No, Larry Niven. Larry Niven's a physicist, and he writes fabulous books. Start with Ringworld. But Bussard ramjet, Dr. Bussard proposed this ramjet that would go through space and have a big magnetic field in front of it, scoop up hydrogen ions, compress them till they reacted, and then it shoots out the back and gives you propulsion, and you don't have to carry your fuel with you. Transformers. We're going to spend a little more time. I was rushing on the last. They're used to change voltage levels. This is a common, how one can commonly look. They'll have this square of, there'll be some ferrous material, okay? Ferrous materials tend to conduct magnetic flux well. Often what they do, have you heard of ferrites? Cores of magnetic fields. Okay. What they'll do, ferrites are this, is they'll often take iron and grind it up into small particles. And then they'll put a bonding agent in it so they can put it back to shape. But what they do is, if it's left all in one piece of iron, it will conduct a magnetic field well, but also conduct electric currents well. And you get eddy currents and you get heating. And the heating is waste, okay? So the ferrites, by grinding up and bonding it back, reduce the currents in it and reduce the heat losses. But you'll have these big iron things, and sometimes they're iron plates, which is another way of getting rid of the losses. And then they'll have a whole bunch of windings. The windings tend to consume a lot more of the space. But what's happening is you got your primary here, and talking about magnetic circuits now, we had a magnetomotive force, and it caused a flux, a magnetic flux to flow. And the magnetic flux would much rather stay inside this piece of iron. It's a much better magnetic conductor. And so it flows over to here, okay, and induces another voltage over here and current.
Can you go back real quick? So you're saying that square-shaped ring is not a conductive material? Like it won't conduct a current through that square? Or
It can be a conductive material, but you want to try to reduce the conductivity, the electrical conductivity. It needs to be magnetic, okay? And so one thing I said, you know, when they grind it up, another thing, they'll build these things up of really thin plates and put some insulation in between so to reduce the currents can flow, because the eddy currents are circulating currents in this. Okay, so you really want to reduce that. I'll go back. Remember I told you I did this when I was a kid? The nails get hot. Okay, you got circulating current in them, and they get hot because they're also an electrical conductor. Yeah, Cam?
I'd always had the perception that the way that transformers work is it was just purely from the magnetic field created in one loop transferring over to the other. Like there was no actual flow of magnetic energy. It always just seemed basically two rods separated by a small distance with a different number of coils, not any sort of connection. I just had never heard of the concept of like a magnetic analog.
Well, and it's usually called magnetic flux. It's analogous to a current if we're starting to analyze it as a magnetic circuit. Okay.
Does it need to be connected, or does that have something to do with the iron ferrous material would have a higher magnetic permittivity than just free space? Or
It's in fact got a lower permittivity. Is that right? it's got a lower permittivity than free space, yes. So that you've got here the iron that the magnetic field can flow through, and you've got the air. And because if the flux flows so much easier through the iron, most of it stays in the iron. And you get very little leakage out into the air. Okay, is that making sense?
I guess I just always had magnetic field as just as a function of distance from flowing current.
Well, and say we have two coils, and we don't have an iron core. This is our primary and this is our secondary. Okay, this guy's going to create a magnetic flux that's going to spread out a lot because it's just air around it. The only part that is transferring energy is the flux that's going through this other coil. So we've got here and here, and we've got all this flux that isn't going through this coil. So they're very poorly coupled. Okay. Now as we bring them closer together, so distance is one thing. The flux lines, as you go further away from this first coil, they decrease in strength. So if I bring the second coil in, the flux lines, I'm going to be getting more of them and more flux in that area. And we now put an iron core in it to try to get the maximum amount of flux generated by this coil to flow through the center of this coil. Am I answering your question?
Yeah, I always understood the principle of having an iron core, just not necessarily an iron core that was physically connected across the two. So I guess just the top and bottom legs of the square there, I've never been introduced to them being physically connected.
Yeah, the iron is a low resistance path, low reluctance path for the magnetic flux to flow. And you want to get as much of the flux that's coming out of this one to go through this one. Now we can take an iron rod and wind both these coils on that same rod and interwind them. Okay? And that works too. There's a whole bunch of different designs, but if you've taken apart a transformer, you will find a rectangular thing in any sort of power transformer. You will. Okay?
Yeah.
Okay. Any other questions? The equations. The ratio of the turns in the primary to the turns in the secondary equals the ratio of the voltage in the primary to the voltage in the secondary, and you invert that for current. Okay? So if the primary has twice as many windings as the secondary, I can put in 120 volts in the primary and get 60 volts out on the secondary. But I will double my current too at the same time. Okay? They only work for AC, not DC. Why? Yes?
Electromagnetic fields can only be induced with changing current?
Needs changing current, yes. Okay? So, in fact, now when Tesla and Westinghouse on the one side and Edison on the other side were competing for whether the power grid was going to be AC or DC, okay, Edison was a big DC guy. The problem was that with DC, we had no means of changing the voltage to higher or lower levels. And so he had to build generating plants that were very close to where it needed to be used. Otherwise, the losses in the wires, the transmission lines, became too large. Well, AC worked with because of transformers. And the fact that transformers work for AC and not DC is why we're at AC today, because it lets us have very long transmission lines between our generators and our users. Now, it turns out now we have very long DC transmission lines. And the reason we do is we have power electronics that can switch, take a DC voltage in and change its level very efficiently with very little loss. So it makes it a very high DC voltage and makes it a very low DC current that we got to transmit. Okay, and so because remember we talked the losses were the current squared times the resistance. We get that. We can now with DC get that current really low, and we can transmit current through DC lines. And in fact, DC lines, transmission lines, work better than AC lines.
Less lossy with DC.
Less lossy. There's some other things we're going to talk about. Skin effect here in just a little while was one of them. Yeah, Monica.
Is there still that reactive power in DC as well?
So if I modeled remember I drew a model up here for a transmission line and had series inductors and shunt capacitors.
Inductors and capacitors go away at DC?
And at DC, what happens, so the impedance of an inductor is J omega L, where omega is 2 pi times the frequency. Now, if that's 0,
And it's a short.
then it's a short. So all those series inductances become shorts. And for a capacitor, it's 1 over J omega C. And when frequency goes to 0, that goes to infinite. So the capacitive coupling between the pair of lines becomes an open circuit. Okay, so you don't have those kind of effects. And in fact, it can make a big difference on the stability of your line, your power line, okay, because you don't have those things. And so,
Reactive power then, right?
what was that?
That does get rid of the reactive power, right? Doesn't it?
Yes, I mean there is. My reason I hesitate to say that is because, so I've got a transmission line here, 2 wires, one going down, one coming back, and it's transferring DC. It still has a magnetic field around it. It's a constant magnetic field, and that magnetic field is storing energy. Okay. So you still need to charge up that magnetic field when you first connect the DC transmission line. You need to put energy in it. But then that energy stays there. And you don't have, other than at startup, you don't have a flow of reactive power back and forth on the line. Is that making sense? Okay. And it affects things, like I said, stability greatly. And DC transmission lines are being used for much higher voltages than AC now. And we'll go into the reason for that a little more here in a minute.
But the DC lines, they would never need reactive power. They're just purely for transmitting power.
Yeah, you don't have this flow of reactive power back and forth through them.
Right, but you would never even need them. They're just
Right.
You don't need them for motors or anything like that.
But the motor still needs reactive power.
Right, but they're not.
So-
You're not plugging something
Then-
into a DC line. You're not.
You can add an inverter when you get to the point where you need the motors, right?
Okay, so
But I feel like they might have a transformer that puts it back onto the AC grid. Like,
Yeah.
I feel like no one's directly, if they're just transmission lines, like purely for transmitting energy, and that's what it seems like the DC would be for.
Yeah, so it
You
could
would
be worthwhile.
never.
The switch from
Connect.
AC to DC, transmit at the long distance, and then switch back to AC when you get there.
Right, that's what I'm saying. There's no
And-
one there's no one running their home on DC power, so they don't need. There's no need for.
no, there's no need for. So at either end of the DC transmission line, it'll get converted back to AC.
Yeah, like
Yeah.
it'll immediately.
Yeah.
AC, so there's not
Capacitor effects.
power.
Just at
Yeah.
You need some
DC,
type of
those
capacitor
effects go away,
that
so
reactive
then you
power
just have
from
the
the AC grid to go on to DC and cause like current spikes.
We'll talk about this.
They do a lot of things with the power electronics and the switching. And I'm sure they've got reactors, or capacitors and inductors in there as part of that whole switching circuit to get the sine wave form to be right, okay? So at either end of the switching, there's a lot of inductance and capacitive stuff going on. Yeah. Did you have a question?
Oh, I think I have. I'll ask you later.
You can ask me now. Yeah, we've got some students on camera here too, and we've got a few EE students, but we've got business students in here. You ask your questions.
So what is the difference between, so when you are doing that transmission with DC and then you want to convert it at the end, are you losing energy there at that conversion point?
That's a very good question, okay? Turns out transformers, which convert AC to a different level of AC, are like 99.9% efficient. They lose a little bit to heating. And the thing that kept us from doing AC to DC and then DC back to AC is it used to be a very inefficient process. And it's only now with the power electronics that we can do it very efficiently, because if it was lossy, we would not be doing it. Okay? So power electronics have been able to make it very, very efficient on the order of transformers. So there's very little losses. Excellent question.
I think I remember seeing on some of the converters they use for solar panels, because solar panels derive energy in DC, so they just drive direct current that needs to be converted.
Yeah,
Some
we need
of
to
those
convert it to
inverters,
power
I
grid.
think like the life cycle efficiency of the DC to AC conversion there was something like 77%. But there's a lot of other stuff going on between. I'm sure the power electronics do a little better on than the solar panels do.
Yeah, and it depends on how much you pay.
Yeah.
You know, you get inverters for, you put, you're on campus here, you put solar panels on the roof of a huge building. You're going to have a big, huge inverter, and you're going to pay a lot of money to make it sure it's efficient. The inverter is what takes the DC from the power, from the solar cells, and converts it to AC. Okay?
Yeah, I did the solar power lab a year and a half ago where we built the power converters for the solar panel to convert the voltage around a bit and then convert it to the 120 volt.
Yeah.
AC. I mean, with the stuff we were using, I mean, our efficiency was like 75 or 80%. But,
Yeah.
you know, just on little like little floods, just soldering it together on our own.
Are you all aware that if you put solar panels on your house, and you put an inverter in and you hook it to the power grid, and you don't have any batteries, but you know, the grid's pretty reliable. We use the grid for storage. If the grid goes down, your panels quit producing.
Yeah.
You get no energy out of your inverter. Okay? What?
If you don't have the battery, you mean?
No, it's a regulatory thing. It's a regulatory thing. Okay, you can have inverters that keep going, but you got to do a lot more different wiring in your house. The problem is, so I live up in the mountains, in the foothills. I can put solar panels on my house, or I can even, power goes out, I can take a generator, plug it right into my outlet here, and backfeed, that's called backfeeding, my whole house. What have I just done though? I backfed into the power grid, so down there a mile from my house a line's down, and a power tech is working on it.
You just lined that wire.
He just thought power was coming from the other direction, and now have created a terribly unsafe condition by backfeeding.
That's why they have to have the power to turn off your
Yes.
solar panels so they can repair the lines and not get gas.
Yes. And so you have to, if you're not going to do that, you have to put in a transfer switch. But right now, the way an inverter creates AC is it looks at the signal coming, the sinusoidal waveform coming in from the grid, and it generates its AC power so that it's the same frequency and the same phase, because it has to be in phase to put it back. And so if that grid power goes away, you lose your control signal, the oscillator, or the inverter quits working. Okay. Okay, this was this Wolfram demonstration project. We did this for power factor. Here's another one, a transformer. Okay, and so we got our primary here, and lo and behold, look at how they drew it. And over here in the graph, we've got our primary voltage in black, or maybe it's blue, and our secondary yeah, it's volts, okay. Our secondary voltage in red. And we can adjust the turns ratio here. Come on. It worked when I tried it before. There we go. So we can change the turns ratio, and lo and behold, okay, so the red is volts. I'm not sure what the other one is. Peak. Okay, so the peak voltage, or the RMS voltage for the input is 10 volts, and the current is 5 amps. Frequency we leave, we'll leave that at 60. Now if we change the turns ratio, and I'm not sure what we're plotting on the graph here is my hesitancy, because if my turns ratios are equal, and if my input voltage is 10 volts, what should my output voltage be? 10, right? And it's not. My output voltage here is higher. And so I suspect we're plotting current on one and voltage on the other one. But this just in red shows voltage and doesn't have a scale for the other one. I'll see if this... It's not telling me more there as to what the scale is. But so I increase the primary voltage, or I'm sorry, the primary turns, and my output, I want to say current, I don't know what I want to say. I think I'm going to confuse you on this one. I thought I understood it, and I don't. Okay, so I'm going to back off on this one because I don't it's not making sense to me, and I don't want to confuse you anymore. Just remember, if the voltages, the ratio of the voltages and currents is equal to the ratio of the windings. Okay, transformers, the real world. How many of you have seen one of these things outside your house? Okay. It's a transformer. What does it do?
Blows up sometimes.
We were just talking about.
Yeah. It's going to do what, Cam?
Blows up sometimes.
Blows up sometimes? Okay, and I've got some videos of those we probably won't get to, but they're on D2L. But it takes a high voltage here. This is the high voltage bushing. You see the kind of wavy insulator here? Okay. The length of that is dependent on the voltage. The higher the voltage, the longer you're going to see that thing. But the primary gets hooked up here, and then over here is the low voltage bushing, where you get 240 and 120 out. Okay? This isn't as interesting, though, as watching a video of them taking one apart. Come on. you know, I run this at home, everything works good, I check my links, okay. Does anybody need to take a break? Or maybe a little overdue? 5 minutes?
Yeah.
Let's do that. And I'll fiddle with this. Connection to the internet site took longer than expected. I wonder if we're starting to see problems because of solar flares. It'll affect communications too. Of course, it's kind of like when your computer starts doing funny things. All of us, or a lot of us, maybe not all of us, start wondering if we have a virus. Okay, start looking for something to blame it on, when it's maybe just be that the internet's slow right now. There you go. That's Nikolai Tesla there. What was that?
It'd be a really bad place to read. It'd be very loud.
Probably not focusing on the book very much.
I guess it's not a picture taken for practical.
No. It's a little staged.
It's not relaxing enough to read.
How many of you have heard the discussions about Tesla's effort to transmit power wirelessly?
Yeah.
Yeah, that was his last project, and he lost funding.
What?
That was his last project of his life, and he lost funding. Yeah.
He does have, he's published some things about it, okay, and I've in fact got one. Technically he was a genius. Marketing-wise, he was terrible. He hooked up with Westinghouse, and Westinghouse was this marketing genius, and in the end Tesla ended up selling all his patents to try and fund his things. It was really genius.
Some of the other things he had was like a death ray, and he created some sort of resonator that caused an earthquake, a small earthquake in New York or something like
Did he?
that.
I wouldn't be surprised. He didn't do things on small scale.
No, so
No.
he's a bit eccentric as well.
Yeah. Like I said, OCD, but a genius too. It's there's a movie that came out here a few years ago, I think, called The Illusionist, or
Prestige.
what was it?
The Prestige with Scarlett Johansson.
The
The Prestige.
Prestige.
That was a while ago.
Yeah.
Okay.
Let me have David Bowie play you in a movie.
Ugh.
You're kind of eccentric. I feel. I think that's
Well, this one was about these guys that were illusionists, and they started, they visited Tesla, and then they came away with this real great illusion where a person goes into the booth over there, okay, and comes out of the booth over there. And it was based on the assumption that Tesla had invented a way to teleport things. Okay, but there's more twist to it than that. It's a good movie. There's a Tesla museum in Colorado Springs that I've never been to, but
Wasn't the way he wanted to do like wireless electricity was to like charge the ionosphere and then like call down electricity whenever you needed it?
Yeah, he saw the return path being through the Earth, but making such a high frequency, and that's what's here is the high frequency, high energy, that it went actually ionized things up in the atmosphere, the ionosphere, if you want to call it that. And so there was a current flow through there, and you'd have a sending tower, and over there you'd have a receiving tower. And they had to be tuned to these certain frequencies.
Has there been any other research into it, or is it just one of those like cool but impractical sort of things?
No, in fact, just in the last few years, you've seen these where you just toss your phone on the pad and it charges.
Oh yeah.
Isn't that more inductive?
What?
Isn't that more inductive?
It's an inductive thing, but until just a few years ago, the power transfer, I should wait till people get back here really, but the power transfer was really small. Remember when I was talking about transformers? Okay, you have two transformers, and one creates a magnetic field and the other one you put in the magnetic field and it gets an induced current. But the air, so little of the magnetic flux goes from here to here that your power coupling, the amount of power you're transferring, is really small. But some guys invented a way to tune these things so you can get a really strong coupling. And it's really amazing. There's a TED talk on it.
I was reading that if you use
Wireless power, look for.
some people are doing, they were doing some research about doing wireless electricity with like a something that would be in each building. It's all magnetic, but if you use something similar to Wi-Fi frequencies, that signal has it has a small amount of losses through regular interference. It has, so basically you could have your house have like a wireless electricity.
Yeah, and we're getting closer to that. So, the two double E's are the ones gone. We'll start talking about them. Okay. So we're talking about wireless power. And we'll wait and I'll show the video when they get here. Nikolai Tesla did a lot on trying to transfer power wirelessly. Okay. But now there are, and this is the last few years, there's a TED talk. What the heck? About wireless power, and they've actually come up with ways to do this so that you can drive your car, your electric car, into your garage, and there's a pad on the floor, and that pad couples to your car and charges it without you having to plug in anything. Okay.
These things like in-use conveniences that save you the effort of plugging something in and not really creating a wireless fridge or anything like that, which would actually serve large-scale practicality.
Yeah, keep ending up with this thing of the farther away you get from a magnetic field, the less coupling you have. We wandered off on a little tangent here. Okay, imagine that. Okay, here's a TED talk talking about transmitting power wirelessly.
Early visions of wireless power actually were thought of by Nikola Tesla basically about 100 years ago. The thought that you wouldn't want to transfer electric power wirelessly, no one ever thought of that. They thought, who would use it if you didn't? And so in fact, he actually set about doing a variety of things. Both the Tesla coil, this tower was built on Long Island back at the beginning of the 1900s. And the idea was it was supposed to be able to transfer power anywhere on Earth. we'll never know if this stuff worked. Actually, I think the Federal Bureau of Investigation took it down for security purposes sometime in the early 1900s. But the one thing that did come out of electricity is that we love this stuff so much. I mean, think about how much we love this. If you just walk outside, there are trillions of dollars that have been invested in infrastructure around the world putting up wires to get power from where it's created to where it's used. The other thing is, we love batteries, and for those of us that have an environmental element to us, there's something like 40 billion disposable batteries built every year for power that, generally speaking, is used within a few inches or a few feet of where there's very inexpensive power. So before I sort of got here, I thought, I am from North America. We do have a little bit of a reputation in the United States, so I thought I'd better look it up first. So definition number 6 is the North American definition of the word suck. Wires suck. They really do. Think about it. Whether that's you in that picture or something under your desk. The other thing is, batteries suck too. And they really, really do. Do you ever wonder what happens to this stuff? 40 billion of these things built? This is what happens. They fall apart, they disintegrate, and they end up here. And so when you talk about expensive power, the cost per kilowatt hour to supply battery power to something is on the order of 200 to 300 pounds. Think about that. The most expensive grid power in the world is thousandths of that. So, fortunately, one of the other definitions of suck that was in there, it does create a vacuum, and nature really does abhor a vacuum. And so what happened back a few years ago was a group of theoretical physicists at MIT actually came up with this concept of transferring power over distance. Basically, they were able to light a 60-watt light bulb at a distance of about 2 meters. They got about 50% of the efficiency. By the way, that's still a couple thousand times more efficient than a battery would be to do the same thing. But we're able to light that and do it very successfully. This was actually the experiment, so you can see the coils were somewhat larger. The light bulb was a fairly simple task from their standpoint. This all came from a professor waking up at night to the 3rd night in a row that his wife's cell phone was beeping because it was running out of battery power. And he was thinking, with all the electricity that's out there in the walls, why couldn't some of that just come into the phone so I could get some sleep? And he actually came up with this concept of resonant energy transfer. But inside a standard transformer are 2 coils of wire. And those 2 coils of wire are really, really close to each other and actually do transfer power magnetically and wirelessly, only over a very short distance. What Dr. Soyachich figured out how to do was separate the coils in a transformer to a greater distance than the size of those transformers using this technology, which is not dissimilar from the way an opera singer shatters a glass on the other side of the room. And it's a resonant phenomena for which he actually received the MacArthur Fellowship Award, which is the nickname the Genius Award, last September for his discovery. So how does it work? Imagine a coil. For those of you that are engineers, there's a capacitor attached to it too. And if you can cause that coil to resonate, what will happen is it'll pulse at alternating current frequencies, at a fairly high frequency, by the way. And if you can bring another device close enough to the source that will only work at exactly that frequency, you can actually get them to do what's called strongly couple and transfer magnetic energy between them. And then what you do is you start out with electricity, turn it into magnetic field, take that magnetic field, turn it back into electricity, and then you can use it. Number one question I get asked, I mean, people are worried about cell phones being safe. What about safety? First thing is, this is not a radiative technology. It doesn't radiate. There aren't electric fields here. It's a magnetic field. It stays within either what we call the source or within the device. And actually, the magnetic fields we're using are basically about the same as the Earth's magnetic field. We live in a magnetic field. And the other thing that's pretty cool about the technology is that it only transfers energy to things that work at exactly the same frequency, and it's virtually impossible in nature to make that happen. And then finally, we have governmental bodies everywhere that will regulate everything we do, and they've pretty much set field exposure limits, which all of the things in the stuff I'll show you today sort of sit underneath those guidelines. Mobile electronics, home electronics, those cords under your desk, I bet everybody here has something that looks like that, or those batteries. There are industrial applications, and then finally electric vehicles. These electric cars are beautiful, but who is going to want to plug them in? Imagine driving into your garage. We built a system to do this. You drive into your garage, and the car charges itself, because there's a mat on the floor that's plugged into the wall, and it actually causes your car to charge safely and efficiently. And then there's all kinds of other applications, implanted medical devices where people don't have to die of infections anymore, if you can seal the thing up, credit cards, robot vacuum cleaners. So what I'd like to do is take a couple minutes and show you actually how it works. And what I'm going to do is to show you pretty much what's here. You've got a coil. That coil's connected to a RF amplifier that creates a high-frequency oscillating magnetic field. We put one on the back of the television set. By the way, I do make it look a little bit easier than it is. There's lots of electronics and secret sauce and all kinds of intellectual property that go into it. But then what's going to happen is it'll create a field. It'll cause one to get created on the other side. And if the demo gods are willing, in about 10 seconds or so, we should see it. The 10 seconds actually are because I don't know if any of you have ever thought about plugging a TV in when you use just a cord. Generally, you have to go over and hit the button. So I thought we put a little computer in it that has to wake up to tell it to do that. So I'll plug that in. It creates a magnetic field here. It causes one to be created out here. And as I said, in sort of about 10 seconds, we should start to see. This is a commercially available color television set. Imagine you get one of these things, you want to hang them on the wall. How many people want to hang them on the wall? Think about it. You don't want those ugly cords coming down. Imagine if you can get rid of it. The other thing I wanted to talk about was safety. So there's nothing going on. I'm okay. And I'll do it again, just for safety's sake. Almost immediately, though, people ask, how small can you make this? Can you make this small enough? Because remember, Dr. Soyachic's original idea was his wife's cell phone beeping. So I wanted to show you something. We're an equal opportunity designer of this sort of thing. This is a Google G1. You know, it's the latest thing that's come out. It runs the Android operating system. I think I heard somebody talk about that before. It's on. It has a battery. It also has coil and electronics that electricity is put into the back of it. And if I can get sort of the camera, yeah, okay, great. You'll see as I get sort of close, you're looking at a cell phone powered completely wirelessly. And I know some of you are Apple aficionados, so you know they don't make it easy at Apple to get inside their phone, so we put a little sleeve on the back, but we should be able to get this guy to wake up too. And those of you that have an iPhone recognize the green center, and Nokia as well. You'll see that what we did there is put a little thing in the back to do that, and it probably beeps actually as it goes on as well. But the screen, typically you use it to light up the screen. So imagine these things could go, they could go in your ceiling, they could go on the floor, they could go actually underneath your desktop, so that when you walk in or you come in from home, if you carry a purse, it works in your purse. You never have to worry about plugging these things in again, and think of what that would do for you. So I think, in closing, sort of in the immortal visions of the New Yorker magazine, I thought I'd put up one more slide. And for those of you that can't read it, it says, it does appear to be some kind of wireless technology. So thank you very much.
So what do you think?
Yeah, it was really cool. I got to see some of that in action actually a couple years ago.
You did?
I was at Utah State. There's somebody working on some of that stuff. So I saw a slightly larger setup for like lighting up a bunch of light bulbs, an array of light bulbs, and then also they wirelessly charge an electric bus that at least by plan should have been in service before now. Just traveling around Utah State, you know, driving students around like a few places along its route to wirelessly charge, like stop at a bus stop for a few minutes, charge up while it loads and offloads people.
There's even talk of putting the chargers in the road, so as you drive, you get the power from the roadway, and you don't have to carry all those batteries.
A little less feasible. You need because you need them like all over the place, and
Yeah.
you're constantly moving. So I think it makes more sense at places where you can park.
Of course, you go to Seattle. How many have been to Seattle? The buses there, they've got these big electric lines, and they just follow these certain tracks. And every once in a while, the big couplers fall off, and the guy goes out and gets his big pole and puts it back on. But you could embed them in the road and get rid of all those wires and have your electric-powered buses. But then people start driving electric-powered cars. So anyway, so other comments?
Looks very similar to a transformer.
It did, it is the coupling of two coils. Okay. Yeah, Cam.
It seemed like it needed to have some sort of directionality. That didn't appear to be something like Wi-Fi, where it's just like an over-air signal. It seemed as if there was, at least in the stuff he was exhibiting, there was a generator, and it was kind of directed, as in the phone doesn't recognize the signal until it's put into the pack. So that would kind of limit its effectiveness for things like cell phones, in my opinion.
And that's a good point. If you look at that square that was in back, okay, you assume the coil is going around inside the square. Okay, so the flux is coming out of that square. Okay, and coming out of that square is right where the TV is. Okay, so if you turn the coil some an angle, you're still going to get some coupling. It's going to start decreasing. When you get to 90 degrees, you're probably going to get very poor coupling. But they're doing some really fancy resonant things here to make two coils that were just a transformer, and they were this far apart, they wouldn't couple very well, but because they're putting some resonant circuitry and a whole bunch of other stuff in there, that's a lot of the flux from here is going through there.
I just had a question about the efficiency. So they were saying the efficiency wasn't very good, like, or I don't know.
It was better than batteries when you think about it that way, but I mean it's not as good as just plugging it in, but you don't have to plug it in. So
you know, and so there's the efficiency. You know, as we've talked about efficiency, is you put this much energy in and you get this much useful work out. And if half the energy in gives you useful work, then it's 50% efficient. The other 50% of the energy is going to losses. Okay? I'm not sure where the losses are in this system. It may be that you put a certain amount of magnetic field here. You have a certain amount of energy stored in the magnetic field, and you can couple and get a certain percentage of that out. But I don't know if that means the rest is wasted.
So we can't feasibly couple with 100%.
Yeah, you won't couple with 100% efficiency, but does it mean that the rest is lost energy or just stored energy? So I don't know on that one. Anyway, any other questions, comments? Yeah, Kim.
When you brought up the wall-mounted TV, not having to deal with the wires, you drill a hole behind the TV. You drill a bunch of holes to mount the TV. One more hole for the wire. I don't think is gonna break my heart.
Yeah.
I mean, there's some like oh, isn't that cool? But like the actual practicality of it was like vastly overemphasized.
Yeah, and they're doing early marketing. It's a fascinating concept that in the coming years is going to really find some really good places for it to be. You know, so a Tesla coil. Watching the time here again. There's a link here that tells you more about this. This is several million volts, and he's just fine sitting there. Okay, skin effect. I've alluded to this a couple times. What's the skin effect? So if I take a wire and I run an AC current through it, the current tends to concentrate on the outside of that wire. Okay? And the higher frequency, the more it concentrates on the outside of the wire, to the point that if you took a hollow tube, okay, you could, and remember when we talked about resistance, you increase the cross-sectional area and you decrease the resistance, right? So normally if I took a wire and cut the middle out of it and made it a tube, I'd be decreasing the cross-sectional area and increasing the resistance. But in reality, because AC flows on the outside, I can cut out that middle because there's no current flowing in it. Okay? And so if we look at the cross-section of some wires, if it's truly a solid wire, then the DC current that's flowing through there, where the frequency is 0, is flowing through all of it, and the effective cross-section is the real cross-section. But if I put an AC current through there, suddenly now the current starts flowing on the outside. And so the effective cross-sectional area has decreased. And the resistance is therefore increased. Okay? You with me? So if we take a long transmission line of solid wires and we run AC through it, the real cross-sectional area of that wire is not the effective cross-sectional area. The resistance increases and we get more losses. And as we go to higher frequencies, we get even more. Everybody with me? Now, when we talked about DC transmission lines, okay, we now go back and take the same wire that for an AC current had a high resistance. If we start putting a DC current through the same wire, we get a lower resistance. And this is one of the advantages of high voltage DC transmission lines, is I can put smaller wires, which is a lot cheaper. I can put my towers farther apart, and I can end up with the same resistance that for AC I need a bigger wire. Okay? And it becomes, anybody ever done anything with microwaves? You know, waveguides. When you do microwave transmission of microwave power, you actually put the power not through a conductor but through a waveguide, which kind of looks like heating ducting. Okay? It's just a box. Okay? And the current is flowing on this outside, and the energy is being transmitted through the electromagnetic field, but you don't need a wire. You just need this hollow box for waveguide. I think we've talked about a lot of this. Here's a good on Wikipedia. If you want to know about the War of the Worlds, or War of the Currents, rather, not War of the Worlds. That was a book. There's Tesla, there's Westinghouse. The transmission losses we've talked about, a big thing. All this is interesting. Edison did a publicity campaign to convince people how unsafe AC was. He would go around taking animals, dogs and cats and horses, and electrocuting them with AC, okay, to show how dangerous it was. And he even, behind the scenes, financed the development of the electric chair to make AC, to paint a very terrible picture of it. Okay, and the first time they tried to use it, they didn't have the currents right, and they didn't kill the guy, and it was a terrible mess. And then later, he even electrocuted an elephant. Okay.
Approximately equivalent to DC current do more or less the same thing?
No, AC, and I'm not sure why, but AC is more effective.
Okay.
Okay, and it's a voltage-related thing, but it's not a real problem. Okay, but he was really pushing back against AC.
He wanted the contracts or something.
Yeah, he did, and he didn't get it.
He was willing to kill for it.
The Chicago's World's Fair in 1893, they wanted to electrify the World's Fair. First time. They went to Edison, they went to Westinghouse and said, how much would you charge? Edison said, and this is what I understood, $1 a bulb. And Westinghouse said 25 cents a bulb. So they went with AC. Lord Kelvin came from Britain and saw it. He'd been a big DC believer, and he saw it, and he changed his mind. So that's interesting history if you want to go read that. We've talked about conversions, AC to AC. Is a transformer. Simple technology, linear parts, simple materials. You cannot change the frequency, only the voltage. DC to DC, you can convert that. Need high-speed switches, diodes, power electronics. We couldn't do that before, we can do it now. A rectifier is what takes AC and converts it to DC. So that lump that you plug your computer into the wall, that's a rectifier. An inverter, that's the sort of thing you have on your solar panels. It takes DC and converts it to AC. The U.S. power grid. It's interesting, the U.S. power grid is really broken into three parts. There's this western, and I guess it's not at the Mississippi, because it's right here. Colorado's in the western. ERCOT, Texas. Texas, a nation of its own. Okay. So even in terms of power grid, okay, they're isolated. And then the eastern United States and Midwest is separate. And when I say separate, what it is, each of these three regions has an AC grid, but they are connected with DC power lines. Okay, so there's no AC connection between any of these three grids. It's all DC high voltage. Why do you think they do that? I mean, it's not long distance.
Is that a way that if one screws up, it'll prevent as much effect on the other?
Yes, it's to isolate them. So if you have a cascading failure in one area, it won't cascade through the DC interconnects. Failures tend to be the frequency gets out of control. You get frequency collapse or voltage collapse. Those are the things that cause an instability. Okay, frequency problems in one is not going to transfer to another one, and even voltage problems, the interconnects are going to take care of that. So it's for isolation. Questions on that? Common voltage levels. Generators can be as low as 480 volts or 220,000 volts. Low to medium voltage in the power world. And the voltage depends on the design. What's the optimum efficiency? Transmission and distribution tend to use higher voltages, lower currents to result in lower losses. We've talked about that. Household. You got 120 volts or 240 volts. In industry, and that's single phase. In industry, we have three phase, and we're going to talk in more detail about three phase. But it's typically 480 volts. Motors that you put in an industrial plant are 480 volts, three phase. One of the really nice things about three-phase motors, and there's some transmission advantages too, but if you build a three-phase motor, it's nice because there is absolutely no vibration. At every point when that motor is spinning, the forces on the rotor are equal. Okay? And a single-phase motor doesn't have that. You're going to have forces pulling the rotor as it spins different directions. But for a three-phase motor, the forces are always equal. So you get a very, very smooth running motor. Okay?
Just a quick question while
Yeah.
we're on the topic of voltages. Why, if when I call up the utility and say like, okay, I want an electrical service at this location, and they say okay, this location you can have 120, 240, 3-phase, you know, but then you still have to put in a transformer. Does that mean that the actual distribution wires are not at those voltage levels?
Right.
Because it seems like if you're putting in a transformer, you could pretty much put in whatever voltage. You could change the voltage. The phases is a separate thing, but
Yeah, so you've got, in your neighborhood somewhere there's a substation. And there's wires come over then into your real neighborhood, because your neighborhood may be this quarter of the city or where that substation serves a big chunk of the city. So it's not necessarily next door to your house. So they still want the voltage coming from that substation to as close as your house to be a high voltage, to cut down on losses. Okay, so it's often, what is it? In fact, I've got another slide here, I think. No, it's on the next set. It's often a few thousand volts, okay, coming into your house or coming into your neighborhood. Then in your neighborhood, you will have a 3-phase transformer. Okay, so all 3 phases come into that transformer. But you typically in your house do not get 3-phase, you get single phase. And they put your house on 1 phase, and if your house is next door, they put it on another phase, and they try to keep it balanced. But then they're right in your local neighborhood, there's a transformer that's servicing 8 to 10 houses that's stepping down to 240.
okay, so the line that literally comes by your house is most likely a 120 single phase.
The one that comes into your house, okay, and in fact, we looked at these transformers, the cans, okay. If you look at the wire from your house to the can, that's 240. On the other side of the can, it's a much higher voltage. Okay. What?
Okay.
Yeah, several thousand volts. You know, we live up in the mountains. We provide power from a rural electric association, so we had to actually pay to get the power poles brought in. It was close before that, and we have a single can transformer on the last pole where our meter is too, that transfers it. And as you drive around and look, you'll see some places there's a single can, some places there's 3 of those cans. 3, it's still got 3-phase coming in there, and it's doing something. What's coming into ours is a single phase. Somewhere back there, that 3-phase got split into single phase, and they just ran wires to our poles for the single phase. Okay? Questions? Comments? Okay, 3-phase power. You can think of it as 3 separate circuits. Okay? And in fact, we could draw it that way. We could say, and this is a symbol for an AC generator. We've got a load over here. Okay? This is ground. And then I could draw another one. If I was fancy, I could even do it in another color. And so this is A, and this is B. And I could draw another one, C. Okay? You guys, can you see this? You probably can't see this. I'll have to remember that. I'll try to do more drawing on the tablet, okay? But we can basically say 3-phase, we have a separate circuit, and another separate circuit, another separate circuit, and then we put them all together. One way of doing that is tie all the grounds together. Boom, and then tie to the next one. And then we say the waveforms for this generator, the waveform is 120 degrees out of phase from the next waveform. So, you know, complete revolution, 360 degrees. And so we have 3 phases. We've got one here, the black line, okay? Well, in fact, let's look at it this way. Let's start at the black line where it's 0, okay? That's VA. They all have the same amplitude, by the way. They all have the same frequency. It's just the phase shift. So the black phase starts at 0 degrees. If we go over now to the red phase, lo and behold, it's 0 at about 120 degrees. And the blue phase is 0 at 240 degrees. So it's like 3 separate circuits, and we can break them up whenever we want, because we just want to bring a phase to a house. But the voltages are 120 degrees apart, and that's critical. So if we start combining these, add all those up, what do we get? The sum of all those, and this is a, see if I can enlarge this one. There we go. 3-phase transmission line. Think of it as if this point they're tied together is ground, and this point they're tied together is the same ground. So you could actually put a wire between these two central points because they're at the same potential. They're at essentially our reference voltage, which is ground. Now you notice the current flowing in and out is current's flowing in sometimes on one of them and out on another. And it turns out if we go and we'll think back on the hydraulics again, if we say we've got 3 pipes and water flowing out of some and into the others at this connection, it turns out that, oh, don't need to do that, at this point here, if I sum up the currents, it's always 0. Always 0. So the amount of current flowing into this node is equal to the amount of current flowing out of this node at any time. Okay, everybody with me there? Now, if I put this wire connecting these 2 points together, how much current's going to flow in that wire?
0.
0. So I don't need it. There's no current flowing in it. I don't need that wire. Or if you're a little worried, I can make it a small wire. So now let's think about what this does for us for a transmission line. Transmission line, if we just take one of these circuits and we're going to transmit, how many wires do we need?
3. Oh, for just one.
Just a single phase, the top one. We need 2. What?
One ground and one base.
One hot and one neutral, you could call it. You need a way for the current, so you got your generator over there, your load over there, a way for the current to go down and a way for the current to come back. So for a single circuit, we need 2 wires in our transmission line. And then what if I put another another circuit on there? Now, and I haven't combined them, I just put another one. Now I got 4 wires. Okay. And if I put another one, I've got 6 wires. Well, if I do a 3-phase, I only got 3 wires. Okay. And in fact, it's even better than that. Because of the way this works out, the wires, you can transmit the same amount of power with smaller wires. So 3-phase has all these advantages with regard to transmission. Besides, like the motor I mentioned, the advantages there. Questions on that?
Well, I heard the technicians talk about the wild leg.
What? A Y? Y in delta?
This is with wild legs. Bastard legs.
But what?
Bastard legs.
Bastard lights?
Or wild legs.
Like wild leg. Like, I don't really understand what that is.
When the 3 phases, the 3 voltage phases are not all the same voltages line to ground.
Okay.
Like one is.
So when it's not balanced is what that is called. Okay. So if it's not balanced, so you got 3 generators over here, and you got 3 loads over here. Now if the loads, and say the generators are identical generators, but the loads over here are not identical loads. Okay? Now we have an unbalanced situation where the current in each of the legs is different. And when the current is different, remember this neutral wire I told you that had no current flow through it? Well, that's really only true if it's balanced. Okay? If it's unbalanced, then you got some current flowing through there. And if it's really, really badly balanced, you got a lot of current flowing through there. And if you don't put that wire there, and I don't know if this is exactly what they're talking about, but if you don't put that wire there, but yet you have these 2 points, they're now at different voltages, and the current is trying to find another path, and weird things happen. Is this what you're talking about, or?
Not quite sure. That's
Call it bastard lights or wild lights?
Well, it's like, so, like a 12208 system is 3 120 legs.
Yeah.
They're all 120 line to ground, and it's 208 line to line.
Uh-huh.
A 12240 three-phase system is 2 120 lines with, I think it's like a 208 line to ground. So
And we're going to talk about those things in a minute. I got some diagrams. But yeah, you got it right. So you got it right. But go ahead with what you're saying.
I think that's what she means by the wild leg. That one, that high leg.
Leg. I thought you were saying line.
Same
Lights.
Sorry.
No, that's okay. I did have my hearing checked this summer. It's still as good as it can be at my age. Okay, I don't need hearing aids, but I still struggle at times. And in fact, one of the things they do for a hearing test is they say words and ask you to repeat the word they said. And if you have losses at certain frequencies, you hear different words. And I've got some of that, so it's probably me. But so phase voltages and line voltages we're going to talk about, and the different legs. Should we just move on and you guys bring it up again when we get there?
yeah.
Yeah.
Well, I guess it didn't really apply to this one, but when we have that topic, I'll bring that up again.
Okay. And we're going to get to it here. No, we aren't. We got 5 minutes left. Y and delta connections. We got these 3 phases. The last connection we showed you was a Y connection. It's sometimes spelled W-Y-E also. It's got this common point that you can consider your neutral point. And that's where you can put a 4th wire. Delta doesn't have a common point. There's no place to connect the another wire. And we went back and told you it has to be balanced. Turns out at the transmission level, when you've got aggregates of all these generators, all these loads, it's pretty easy to be close to balanced. And those are often in a delta configuration, the transmission lines. So you have 3 wires. And if you go look at high voltage transmission lines, you'll see 3 wires separated from each other. At each of those points, you may see another 2 wires instead of 1. So you may see a pair here, farther away, a pair here, and farther away, a pair here. That just means you've got 2 wires at the same potential next to each other. But look at them and you will see 3s. Okay? Delta 3-phase system. Line 1, line 2, line 3. And let's see if I got, yes. Here's a Y connection. And Eli was just talking about these voltages. Okay? So we've got basically 3 voltages coming out from the 3 ends of the Y, and then we've got a neutral coming out from the center. From any leg to the neutral is 120 volts. Between 2 legs is 208 volts. Don't need to worry especially about the voltages, but Y and delta are important to understand. So the transformer outside your house comes in with single phase, a few thousand volts here. It goes in the secondary side has really got two windings, or maybe a better way to say it, one winding with a connection right at the center coming out. So you bring out a neutral connection, and so you can take line 1 to neutral, and it's 120 volts, or line 2 to neutral, it's 120 volts. If you look in your breaker box, there's 2 rows of breakers. You try to get those balanced so line 1 and line 2 have equal loads on them. But if you go across line 1 to line 2, you get 240 volts, is, for instance, where your electric dryer or your oven would hook up. Okay. This is what a 3-phase phasor diagram would look like. They're all separated by 120 degrees. They stay separated by 120 degrees. They have the same magnitudes. They rotate together. And we can start doing fancy things with the rotation that we're not going to do in this class. So, questions on that?
We're going to have a topic to talk about the faults, like line-to-line fault, line-to-ground fault. Okay,
you can get, so there's phase voltages and line voltages. In faults, a fault occurs when current is flowing where it shouldn't be. That's a fault, pretty much a definition. If you're being electrocuted, you're a fault. Okay, the current's flowing through you and it shouldn't be. But you can get several different kinds of faults. You can get a line-to-line fault, okay, where the current, the 2 separate lines from the 3-phase, there's current flowing between them somewhere where it shouldn't be. Or more often, you can get a line-to-ground fault where, for instance, a branch of a tree is touching one of your lines and giving you a path to ground. Okay? Is that... I don't know that we'll talk much more about that. When it comes to troubleshooting, the difference makes a difference, and they have different characteristics, and there's ways of telling. So I asked you at the end of the day here, I should let you go. We got a minute left. I mentioned at the beginning of class when not all of you were here, but one thing I'd like feedback is, am I boring you, or am I losing some of you? Because we got people from a lot of different backgrounds, and that's the hardest thing in this. And I feel like today that I was boring you a bit. Okay? And it's okay to say, yes, you were. Or at least I was bored. That doesn't mean everybody was. But I feel like I was boring you today.
At times.
At times?
It comes and goes. It's hard with the 2.5 hours.
It is hard with the 2.5 hours. Monica?
I mean, just whenever we're going over like the more denser material, like going over phasors and stuff, I guess it's as boring as like a normal class, like just going over like basics and stuff. But I generally am not bored because it's a very conversational class, and we're discussing just general topics and interesting stuff.
Okay.
Not necessarily equations and sine waves.
Okay.
I think some of the tangents are interesting to me, involved when they're not interesting to me per se.
Okay.
It's a little easier to just because I know it's not relevant to the course, and it doesn't, and then it's whether or not I'm just involved in whatever topic we have to do.
And I try to keep my tangents somewhat related.
It's somewhat related.
Okay.
Once I recognize the pertinent detail of the relation, then I guess
Okay.
go in a different direction.
Anything to say? Okay, that's fine. You don't have to say anything. Okay. In the next week or two, you're going to get your first homework. It's going to be, we're going to start looking at case studies of, what was that? I just ran across one today, in fact, that I was going to, I'm just reading an article. So I tend to read news articles and then expand those into case studies, like the German situation. We're going to start with an article from The Economist from last year that my son sent me that we used last year, and we're going to expand that. It's fascinating, complicated, puts everything together. So you're going to start seeing some homework like that. What?
No.
Not me? You might be interested. As I've told the other students, we're not going to be doing traditional problems. We aren't going to do solve equations and stuff. We're going to be looking at case studies and what she means is she's auditing it, okay? And she doesn't have to do it. But I'm hoping that I make it interesting enough that she'll want to dig in, and we'll certainly come back and talk about it in class. And again, thank you for your questions, okay? And the other part of it is we've got students out there who, if they're not understanding it, they can't ask questions. So if you have a question, and you think you're the only one that has a question, you've probably heard this from teachers before, there's a really, really good chance you're not the only one that has a question. So ask it. And I include you. Okay. So that's what I got. Have a good weekend. Go home for the warm day tomorrow. Had snow at my house last night.